All right, hello everyone, and welcome to day 3 of the IAIFI Summer Workshop. We're going to go ahead and get started. Our first talk today, we're very excited to have Christoph Weniger here. Christoph is an associate professor at GRAPPA and the Institute of Physics at the University of Amsterdam. He has been leading the charge in simulation-based inference at various applications in physics. And this morning, he's going to tell us about how to navigate complex models. Whenever you're ready, Christoph.
Okay, great. Thanks a lot for having me. Right, so the title was initially Navigating Complex Models, Neural Networks for High-Dimensional Statistical Inference, but what I actually want to do is to focus on a specific way of doing statistical inference with neural nets, and that's implicit inference, or it's called simulation-based inference or implicit inference. I will spend some time trying to explain you the general difference between implicit inference and explicit inference without reference to neural nets. And then what we actually can do with deep learning in that context, and where interesting applications lie, and what are the upsides and what are maybe the downsides. Okay, so the context in which this happens in my case is like this is astrophysical data. I'm coming from like the high energy astrophysics front, so I spent a lot of time in my life analyzing gamma ray maps like this. But the challenges that one has here are also applicable to other data sets. And in general, the problem is if you have complex data, we require quite diverse analysis methods like object detection, object classification, population analysis, model selection, and so on. And the challenge is in some sense, although there are often very specific methods to do one or the other, often these analysis challenges occur simultaneously. One piece of data where you want to do object detection plus classification plus maybe population level analysis. And traditionally, one would have maybe focused on a specific paper on one challenge and then use the output as input to another paper and get circular effects. Good, so what happens, or what often happens is the following. So we have a great idea, a model that we want to test with an experiment or with an observation, and then we have a measurement or observation, compare measurement results with predictions, and obviously the insights that we get ideally refine our models. But what happens quite frequently is that instead we just get analysis-dependent results, and different groups end up with slightly different answers, and it's very hard to agree. And so a thing that often happens, and I took this from nice lecture notes from Uberto Picino, is the following. So you have a complex scenario, noisy data, unobserved variables. You formulate, in principle, a pretty realistic model, which however can't fit to the data, because inference is not tractable. And then you simplify your model, maybe a lot, and now at some point it's tractable, and then you can fit it to the data, and you're happy and write the paper. That's certainly something that one observes often, and certainly something I have done in the past. And I mean, it's not anybody's fault, it's just like what you have to do to make progress in the first place. So, but often you can ask the question, okay, maybe I simplify too much, maybe it's hard to believe that the results are as good as they look like, and so on. So one question is, what does actually intractable mean in this context? So what type of problems are intractable? And how are they intractable if you use implicit versus explicit inference techniques? So I first want to spend some time telling you what is implicit and explicit inference, or likelihoods versus likelihood free versus likelihood based, or simulation based versus likelihood based. So just to understand, who knows already the answer anyway, please raise your hand. Okay, so you will learn something new. And this first part will have nothing to do with neural nets, but will have a lot to do with like basic statistics and methods from the 80s. So first thing is to understand something that you already know, which is the point. So statistics or inference is about probability distributions, right? And there are two things one can do with the probability distribution. Let's say the Poisson distribution. One thing is you can evaluate the density, right? So if you know its parameters, and if you know you observe like k events, you can evaluate just this expression, the Poisson distribution, get the answer, a single answer. And then there's another thing you can do with the same probability distribution, which is simply to sample from it, right? So if you know its value, lambda, the expectation value, you can generate random samples. And these are two aspects of the same object. But generally, you need different computer codes to do this. So you would either have a computer code that takes k and lambda as input and spits out a number, or you have a stochastic program that takes lambda as input and spits out random samples. If you have a probabilistic programming language, suddenly both happens like in the same code. But generally, people spend some time either writing this or writing that. So now starting either from here or either from there, one ends up with different inference strategies. And to that end, I want to use a very simple example that actually is not that simple. So imagine we just look at the trajectory of a ball that we throw in from here with a specific angle phi ini, and uniform gravitational field. The ball flies like this, hits the wall, and we observe where it hits the wall. And then we ask the simple question, what do we actually learn from one observation about the initial angle, or maybe from multiple observations, or maybe only observations in a specific detector area where it happened, right? That should be a simple problem, right? Okay, so let's start easy. Let's assume we only observe one hit, and we only care about measurement noise. We have an idealized scenario. We know the initial velocity. There is no like weird wind. Then the likelihood function would be simply a normal distribution with some measurement noise, and the physics model, like our physics simulator, is here the expectation value for where we expect the ball to be. So all the physics happens basically here. And now we can do either implicit inference or explicit inference. Explicit inference would mean we evaluate now the normal distribution along this initial angle. We get two peaks because either for fixed velocity, the ball can either go straight or like this longer way. So it's bimodal distribution in this case. We multiply this with the prior, we get posterior. So this works pretty well. And if you wanted to go the implicit inference route, we would do the following. We would randomly draw from some prior distribution for the initial angle, put this into a simulation code, which basically simulates the trajectory and then add some measurement noise and returns X. And then if you do something called approximate Bayesian computation, which is a technique from go back to the 1980s, we would just keep simulations which are close enough to the actual observations. Here 1.4 is the height. And if you then make a histogram of the angles that have led to these accepted simulations, we get two peaks, so bimodal distribution. In the limit where epsilon goes to 0, and we have an infinite amount of simulations, we get the same posteriors that we would have got from here. So that's the simulation, the simulation or implicit inference way of doing this. So now let's do it slightly more difficult. So let's assume now actually we don't know the initial velocity. So there's some uncertainty in the initial velocity. And let's say there's a random field, a random wind, right? So we might have wind gusts, spatially varying and temporarily varying. So this can be a very high dimensional object. Now calculating the marginal likelihood would require to actually integrate over all wind configurations and over the initial velocities. Depending on the details of the models, this can be very nasty and somewhere between difficult and intractable. And now the explicit inference way to proceed would be to assume maybe this is a Gaussian random field, and then being smart, maybe along integrating along like paths in the Gaussian random field or something like that, or trying 3 different wind patterns and seeing how they affect the result. So things can become quite tricky on that front. If you go to implicit inference, nothing really changes. We just extend our algorithm by, so beyond drawing from the initial angle, we also draw from our wind configuration. This might be actually observed wind fields that might have a database of 10,000 like possible wind configurations. And then we draw from the initial velocity, simulate, and the only thing that really happens is that now our predictions are a bit blown up. So in some sense, this adds on top of the variation, on top of the measurement. We still get a histogram. Now the posteriors are a bit wider, but that's it. So nothing really became more complicated. And this is now a problem that might be formally like 1,000-dimensional or whatever, how many parameters you use for your wind field. Okay, now we can go a step further. Let's assume we have multiple hits, and we only keep the hits that hit the wall. Then the likelihood function can be still written down like this. So we have this intractable integral for each of the hits. Then we have this normalizing constant here, which says something about the probability that a ball would have hit the wall in the first place, given initial angle and initial velocity dispersion. And so, but on top of that, so this is something with simulations we could solve in some sense. We just simulate until we have as many hits as we observed accepted. But then the problem is we end up with a list of possible hits. And then this very simple ABC trick that I explained before. So just picking observations that are close to what you observe becomes very inefficient because you need to like be close to some point in a high dimensional space. So what this immediately suggests is, okay, maybe we replace this by a smart data summary. So we could look at mean values or variances. So the mean value of all the hits that you get here, or the variance of all the hits that you get here, and play the same game that I played before, ABC. So we can again. So now this here is not the height of the ball that hit, but the average height of all the balls that were hitting the wall. We can still use this information now to get posterior. And that's it. So what you see here in this ABC context is that we can solve this, in principle, very difficult problem suddenly. But the difficulty is to come up with good data summaries because they are not like automatic here. I just guessed it's a mean. The variance is probably a good idea. But they are probably not optimal compressions of the data. And the other thing is this epsilon to 0 limit. So I accepted here simulations that are also not exactly what we observed. So we need a lot of simulations to make this go away. And this is what, so these kind of things are the reasons why ABC hasn't been used much in the past. Pretty niche. But neural networks help a lot on both fronts. So they can be used to actually learn data summaries that are optimal or close to optimal. And you can just use density estimation in various ways to, in some sense, do the epsilon to 0 limit here. And this is how simulation-based inference essentially works. There are also lots of like challenges in using this for various problems, which I will partially try to address a bit later. But let me first explain you how this can look like in the context of deep learning. Well, typically the trick is now we want to learn some representation of a posterior, low-dimensional posterior, or any posterior for parameters of interest given data. Posterior, it could be marginal likelihood. And what we have to do for this is to come up with loss functions such that if you minimize them, that the thing that we minimize, the network that we minimize approximates the posterior likelihood or ratios of posteriors to priors. And there are many different, I mean, these are just 3 examples. There are many different examples, many ways we can write down loss functions that lead to the same answer formally. They all tend to lead to different algorithms with different benefits and downsides. But all these SBI algorithms or implicit inference algorithms, no matter the form, share in principle the properties of approximate Bayesian computation that I mentioned before, beneficial. What you see here is also that the averages that you have in these loss functions here are draws from the simulation model. So typically draw first some parameters, you plug this into a simulator, parameter Z, you plug this into your simulator, P of X given that, and then you draw from the simulator. So this here in the past, in previous example, this would be drawing initial velocity and then plugging this into the simulator and getting hits on the wall. Good. So the posterior density estimation has been over the years the most popular way of doing things. Nowadays, score-based techniques like training diffusion models to act as posteriors also become more popular. We have spent a lot of time doing posterior to prior ratio estimation, which has certain benefits and certain downsides. I will just explain how this here looks like. So one example is here that we liked to use a lot in the past. Strong lensing image analysis, because it's really hard. We'll always tell you more about how hard it is. The next talk. So here I just show you a simple example. So you see here a background or galaxy that is lensed by unknown lens, and the lens galaxy you don't see. And now we want to train a neural network to tell us parameters about this object given this observation. So the way this would work is we draw parameters Z from the prior. In this case, this is like a 15-dimensional parameter space. Plug this into our lens model. This predicts then how the average flux looks like in this plane here. We add on top of the measurement noise. And in this way, we get a lot of data parameter pairs. And then we initialize a real-valued network that takes as input parameters and data and minimize this particular loss function. Doesn't really matter what this loss function does, but the point is you can analytically show by just taking the functional derivative, if you want, with respect to the network, that the thing that minimizes this loss function will be the posterior to prior ratio. So once you train this, you get a network that is the log of the posterior to prior. And since you know the prior, you can just yeah, access to posterior. So that's something that one of the ways to do this. So how does this connect to ABC? And for the ABC story, I said, okay, we have the problem of getting data summaries, and we have the problem of doing this epsilon to zero limit. Well, typically a network architecture that one would use in this context looks like this, or can look like this. So you have this input Z, so the parameters, and X, which would be the images. And then there's typically some smart embedding network, which is very problem dependent, which is able to like extract the data summaries with information about the parameters that you're interested in. So maybe this would be just a convolutional neural net. So this brings then the input down to, let's say, 10 or in this case, 4 data summaries. So this thing is the thing that learns data summaries. And then we concatenate these data summaries with parts of the input variables we are interested in. Let's say we are just interested in one parameter out of the 15, and then in another parameter out of the 15, and then maybe in the correlation between the third and the fourth parameter. And then we plug this together, so the parameters together with the data summaries into MLPs, which do the second thing. So the MLPs would learn the density distribution of points. And once you know the density distribution, you can evaluate this along the line and get basically to the epsilon to zero. And if we start training this network, you see what happens here. So this is like how this looks like internally while you're training. Parameter for some arbitrary model that I used here, toy model. And this is a data summary. Initially, the data summary, you see this was like not correlated with the parameter at all, so it's not a useful summary. But if I start training the model, there's some correlation being picked up. I made it such that it's bimodal distribution, so the parameter enters quadratically. So it looks a bit more interesting. And then and what you see in color is basically then the second network, the MLP, that starts learning the density distribution of points. And you should focus on the red points, which are the correlated points. Blue points are just for contrast, scrambled points. And once it's trained, you can just read this MLP off along the data summary that you actually got, that you get to posterior. This is something here in a very simple example, but it basically something like this tends, in some sense, to happen in all cases where you start to use simulation-based inference. Sometimes the embedding is kind of glued together with the MLPs, the density estimator, so you don't have obvious data summaries. But when we do things typically structured like this here, it's useful to have low-dimensional data summaries that you can compare with low-dimensional parameter summaries. Good. So that's all to know maybe on that front there. Then I should say, okay, this is like a very tiny subset of what actually neural estimate looks like, or simulation-based or implicit inference looks like. I recommend you to look at the website of Siddharth. So he collects like what's going on on that front, and there are like probably hundreds of papers now, at least 2 good review papers about the topic, one pretty recent one, and also quite a few code packages, including our own Swift here. It's one of the code packages which specializes on neural estimation. Good. So I have 12 minutes left. Right. Good. So how does this? So if you take anything away from this talk, maybe this distinction between implicit and explicit inference and the reference to ABC. I think it's always very useful to think about how ABC behaves and how chi-square fits behave, and what are the upsides and downsides of both things if you start thinking about which neural net, which deep learning approach you might want to use for analyzing data. So already before going through the results, one thing that is very difficult, or tends to be very difficult, is one of the challenges here is often you need an embedding that actually extracts all information from the data. If you have a likelihood function, in some sense, it has already all information from the data. So if you have a low-dimensional problem, but a super high-dimensional parameters image, then it tends to be very difficult to find embeddings that extract from the millions of pixels as much information as you would just get from a likelihood. So some problems that tend to be very simple on the likelihood front can be very difficult for implicit inference sometimes. Anyway, so I will show you now some examples. So first of all, there are a bunch of people doing all the work, mostly at Kappa in Amsterdam. And we started maybe a couple of years ago looking into statistical inference problems. I didn't add papers from this year, but There are also some, I will highlight some here. So I recommend you to look at this if you are interested. I want to here just highlight not specific work that we did, but specific aspects of, again, implicit inference, and then exemplify some of the papers. So one of the things that I already emphasized is marginal inference. So one thing that is very difficult with explicit inference, but tends to be, or is easier with implicit inference, is to directly look at marginals. So as I said, when you train a neural network, it's basically up to you what parameter you show to it. And so you can decide, okay, I'm interested in the 3D posterior for the first 3 parameters, and then the 2D posterior for these 2 parameters, and then another 2D posterior for these 2 parameters. Or maybe lots of 1D posteriors. Or I'm interested in the full problem, or maybe like split up a problem with 1,000,000 parameters in 1,000 and the rest. So there's some flexibility in focusing on what you're interested in ignoring like random wind patterns. This starts to receive more attention. It's a general property of implicit inference, but it's not like really systematically exploited. One trivial example that one wouldn't think of in this context, but which is like a version of this, is that you can obviously use FBI or implicit inference very efficiently for model selection. So it's like, I mean, it's just like training a classifier. But this falls into this category of looking at marginals, because formally to get the likelihood of your data given some model, you would have to marginalize over all the parameters of your model, right? And then compare it to other models. So one example is where we use this, here with constant Karchev, is to look, for instance, at supernova from the Carnegie supernova project. And the goal was here not to do cosmology, but just to show that one can compare different dust extinction models, or dust models for a supernova. And so basically the trick was to look at different scenarios where the dust absorption either depends on the hot galaxy mass or not, or where it randomly varies from object to object versus not. If you write down the number of parameters, it's about 4,000 parameters that we kind of marginalize over this way, but the network doesn't really see this. It's just like trained as a classifier. And yeah, what we found in consistence with like previous literature is that there's no strong evidence for like variable dust this extinction from object to object. Yeah, Koziev wrote also a few other papers on that one. So one recent one was comparing results from implicit inference with HMC results. Another aspect is amortized inference. So usually, and this is something that is emphasized a lot. So there's also an entire review article about this recently. Once you train a network, you can apply it, because it was trained on a lot of simulated data that looks in all kinds of ways. You can apply it more or less instantaneously to new observations and get pretty quickly results. Depending on how you train your model, if you train it with a normalizing flow, once you have conditional normalizing flow, you can sample very quickly from it and maybe generate thousands of samples within a second. And so once you have the signal, you might instantaneously get posterior samples. The downs, okay, that's a benefit if you're interested, if you have a lot of data that you want to analyze quickly. But the challenge is that you need also to train a network to give you all possible answers, right? So you need typically deep network architectures, you need a lot of training data. And often we are in a situation where you actually just have a single image or a single piece of data that you want to analyze carefully. So in some sense, it's not efficient to solve all possible problems first, just to then solve the one that you're interested in. And this falls into this kind of, yeah, solution to this is sequential simulation-based inference, which is a research field. 2016. So there the idea is you start initially drawing samples from your prior of your models, but then what you do is you train first approximation to the posterior, and then you use this approximate posterior, which tends to be then very wide still, because the network hasn't really learned optimal summaries yet for the specific observation you care about. So yeah, then you use the suboptimal posteriors as the new proposal distribution, and you iterate. So in this sense, what you see, so in the context of strong lensing, this might be the target. Initially, we draw our parameters from the entire prior space, but then we kind of focus more and more sequentially onto parameters that are consistent with observation. And then in the sixth round, it might look like this here. It's pretty close to the observations. And if done right, this here gives pretty precise answers to things like the Einstein rate. So we need to do this in a sequential way. A tricky aspect of this here that I should emphasize is that obviously it's a problem principle that you use the posterior as a prior, right? So you double count data. So there are different strategies then to overcome this. One is to simply divide by the proposal distribution divided by the prior again, but it depends on the situations where this is possible or not. And I will come back to this later. But let me first show you what one can do with this. So one thing is one can do, for instance, sequential inference for gravitational waves. So what you see, this is the target signal here. This here are simulations. Initially, they vary. You see this especially, you saw this initially, time of coalescence was going back and forth. So after a few rounds, actually, the signal simulations become closer to the actual observation. This here is without noise. This is actually what the network sees, so noisy data. And things like here, the luminosity distance then converge step by step. You can see this also here. So for instance, the chirp mass over multiple rounds becomes very tightly constrained. And typically such an approach requires, like in this case, 10 to 100 times less simulations than MCMC, which is beneficial if the simulations are the part that are small. There's also recent work by I mentioned this maybe later. So there's if you accelerate your simulator, and if that's not the bottleneck anymore, you can beat these methods also. Yeah, so it depends on where you are in the spectrum. So this here took like half a day to run, which was beating MCMC methods that were taking a few days before, but nowadays the MCMC methods can also go down to a few minutes. So it's ongoing research. But one thing that is interesting is that the method is very scalable, as I mentioned before. So now if you say, hey, let's take just 2 gravitational wave signals on top, which isn't necessarily something that happens right now, but that will happen more and more in the future with Einstein telescope and so on. So let's take 2 on top, then instead of 15 parameters, we suddenly have 30 parameters. And the MCMC runs take at least like a couple of weeks to a couple of months to converge. But if you run the simulation-based inference, we have within a day or so answers, which look pretty converged. So what you see here is the like 1D posteriors for all the 30 parameters, the overlapping analysis where we like take into account all the parameters at once. The overlapping analysis results are typically just slightly wider than the ones that you get if you pretend that you know the other signal perfectly. Right, and this scales pretty well to more and more signals. So this also works if you use 3 or 4 signals. It doesn't really explode the computation cost like they would do for MCMC in this case. Good. So one of the things I wanted to come to, so maybe 5 more minutes or something, is now the challenge. Okay, we have sequential inference on one side, so this focusing simulators on actual data, so to get precise answers. And then we have this property of marginalization. You can, in principle, look at marginals and focus on parameters of interest. But the difficulty is somehow to bring both aspects together. And the reason is it's quite simple. So I said earlier that if we use sequential techniques, we have to correct for the fact that we used the wrong proposal at some point, right? We used something that looks like the prior, typically, rather something that looks like the posterior, typically, rather than the prior. And that becomes difficult if you look at marginals, because marginals are implicitly integrated over the prior, right? So if you look at the marginal posterior for one parameter, you integrate over all the other parameters. And then you kind of glue the wrong proposal into your answer, which is bad if the parameters are correlated. So what we propose is, instead of using proposal distributions that look like the posterior, you can just use truncated priors. So we essentially just take the prior and then cut away parameters that are clearly excluded with high significance and keep the rest. Then within this region, we still sample from the prior. And if you think about like how this affects marginal posteriors, then if you do things right, it should not affect them at all. So the way this looks like is, initially your prior space might be uniform. These are 2 parameters, and then if the 2 posterior sits here, the training data and several rounds will start looking, or will be more focused on the parameter. Okay, so now that's straightforward, but now the devil starts to sit in the detail. So now the question is how to do that actually, and what are the downsides and upsides? So one way would be, if we estimate each parameter separately and then constrain them, then the training data would be sampled from parameter spaces like this here. So we would have like box-like truncation, because this might be Z1, this might be Z2. We truncate them separately, so we sample from the box. Or we could take into account parameter correlations. Then we have to actually learn with a neural net the higher dimensional hysteria. It's just 2D, that's not hard, but might be 100D. Then the benefit is we exclude more of the parameter space that is inconsistent with data, but we have to model correlations. And so I wanted to show you in the last few minutes a few examples where we use different truncation strategies. So if I have a plot like this, this will indicate we just learn all the parameters and use them for focusing. Let's show something like this. This means we learn, in this case, 9 individual 1D posteriors and use them for truncation. So it will look like this. That's actually what we did for all the gravitational wave examples that we had so far. So we never learned a 30D posterior, we just learned 31D posteriors. Or you could do like 3D plus 1D, 5D truncation. So you could split up parameter space and things that you care about. I want to emphasize that the difference here, so the choices that you make here don't affect what kind of posteriors you can learn. So you can zoom in like this here, or you can focus your simulator using this strategy, and afterwards still use the training data to study correlations between parameters. Okay, so you don't destroy correlations. What you actually do is you are doing a better or worse job in reducing the variance of your training data. So just as an example, again, this here is from lensing images. Here this time also with lens galaxy included. So untruncated, then it just looks like random. And then if we would focus on observation, it kind of looks like this. And if we just truncate so just this box-like truncation, then the training data still has a lot of variation, simply because we didn't account for parameter correlation. So the entire things cannot exclude regions of the parameter space, for instance, that lie here, right? Because you have the box that tries to contain the full posterior. But if we model like a 22-dimensional posterior and use this for truncation, we get pretty low variance training data. Good. So, and what's the benefit of that? Well, the benefit is now we can look at more complex models. So this would be a strong lensing image with 22 parameters, including the lens galaxy, the source galaxy. And then we have 2 more parameters for a subhalo position that might sit here, and for the mass of the subhalo. So we solve a 22-dimensional problem to zoom in, and then we solve a 2-dimensional problem to find the subhalo position, the 1-dimensional problem to find the position. So what you see here is that this block-wise sequential inference allows you to look at individual posteriors correctly marginalized over the rest. And the main reason to do the focusing is to reduce the training data variance, which makes posteriors in general more precise. One more example, which is maybe the most interesting one, because it looks very simple, but it's really difficult. Just point sources. Just like imagine you have an image with a bunch of sources. You're not even with a background. This is a transdimensional model. If you don't know how many sources there are in the first place, you might have a luminosity function, a spatial distribution for these sources. So this is like a 3-dimensional population model in this case, which tells you how many sources are there, how much are they spread over the image, and what's the luminosity function. And right, so in simulating this image is pretty simple. We just sample from the population parameters. We sample the number of sources. We generate random sources with the correct parameters and put them on the sky. So how would sequential inference look for this, right? So that's an interesting question. And I should say these problems are all over the place if you try to analyze physical images or data. Because typically you don't know how many objects you have. Typically you have a lot of objects that you just didn't detect. Good, so let's say this is a target observation, and there are some round 1 training data would look completely random, right? Sometimes close to the disk, sometimes spread over everything. Now, if we would want to truncate, we should both at the same time focus on more realistic or more reasonable population parameters, but also somehow fix at least the bright detectable sources in place, right? So what you see here is that in round 2, this is actually happening. So in round 2, The bright sources here, which the network in this case thought they are pretty well detected, will stay in place, whereas the rest still randomly varies, right? So this is how trans-dimensional inference can look like. I'm not going to tell you how we did it, but I want to explain you what happens under the hood in some sense. So this is now visualizing like the correlations that we study. So we have 3D posterior for the 3 population parameters. Then we have posteriors for the individual sources. We don't model the correlations between just like the individual properties. And then there is a part which is the the sources that were not detected, which is not modeled, which is just randomly sampled. So sub-threshold sources, detected sources, which you can kind of put in a catalog. And then if you're on round 2, what happens is we have this detected sources, plus we have the constrained images where the detected sources don't vary anymore. They don't depend on the population parameters anymore, only the sub-threshold sources. And then we can get constraints on the population parameters by combining the constrained images, which have lost information about the population parameters from the bright source fixed, together with the sort catalog, which knows everything about the bright source. And if one does this correctly, so basically we replace posterior here depending on the full data, by posterior depending on the constrained data and the cutoff. If one does this, then one can get population parameters, population parameter constraints based on the detected sources and undetected sources, and consistent with what we plugged in initially. Right, so under the hood, this trains 4 networks, which basically do detection of sources, plus study the sensitivity of the source detection network, plus a network that interprets the source catalog, plus a network that interprets the random gamma ray emission. And so you can then have optimized networks for each of these problems. And the nice thing is it's very similar to how you would have traditionally analyzed image. I'm not sure if this is the optimal way to solve the problem, but it's one of the few ways to do this. Another way would be trans-dimensional Hamiltonian, trans-dimensional Monte Carlo. I don't have time to go through this. So high-dimensional inference is also something we looked at. I want to maybe end with this slide here. So this here is something that my PhD student, Noemi, and I want to put together. So just a comparison to number of parameters, number of simulations needed for different analysis problems related to gravitational waves. These are 21 centimeters. Typically, you need less simulations by 1 order of magnitude, more or less than magnitude. One of the hopes with all of this is that simulation-based inference will allow us to look at problems which have a lot of parameters, whereas likelihood-based inference tends to become complicated now. That said, likelihood-based inference is something where still also, of course, a lot of progress happens. So, for instance, for gravitational wave parameter inference, there's been recently a lot of work on just making the simulations faster and the inference goes smarter. So you can now do what we do like in half a day with simulation-based inference with 1 minute running MCMC. This works for 1 gravitating wave, so I'm not sure if it works for 2. So we can, so both sides, it's worth to optimize. Then on the Bayesian, another example, which I still find like immensely impressive, is a 10 million dimensional problem for reconstructing initial conditions of the universe. This is Borg. So that also works. It just requires a very fine-tuned Hamiltonian Monte Carlo. So depends on the problem, what works well and what doesn't. These are my key points. I think the main point I want to make here is, the hope with this is really for me to analyze, to get to the situation where you can make your model arbitrarily complex and actually still compare it to the data, arbitrarily realistic and compare it to the data. There are still a lot of challenges, especially in the sequential inference for trans-dimensional models for it. But it's something we're working on. So if you're interested in this, also talk to me afterwards.
Thank you, Christoph, for the great talk. We have time for just a couple of questions. Let's see what we're right here.
Hi. A comment and a question, a comment real quick. I would like to re-emphasize what you put on the second last slide about MCMCs. Really, they can be really fast. And we've done a ton to make them fast in the particle phenomenology space. And they end as slow as 20 days. So, and we do about 100 parameters, hundreds of observables, and they're pretty fast. The second thing is really about the model comparison you flashed really quickly. In a Bayesian framework, it's really difficult to do model comparison unless you can compute a Bayes factor or something of that sort. And really the problem is the number of parameters to increase the complexity of the model. You could fit basically anything. So I did not understand how you do that without actually trying to compute a Bayes factor or an approximation of the Bayes factor.
Essentially, what happens when you train a network, it doesn't learn the Bayes factor, but it learns ratios of Bayes factors. So so that's just what comes out if you train, for instance, a binary classifier. It would learn the ratio of two Bayes factors, depending on the problem that you specified. So that's what happens. You don't have in general access to the actual evidence. You just have access to evidence ratios. Maybe regarding to your first point, I agree that in some cases MCMC can be extraordinarily fast, but there are certainly cases where it's also just the bottleneck. And this is, I mean, these are the situations that we try to focus on, which are the more interesting. So one thing that I didn't mention here, which is nice work with somewhere with so nice work with one of my PhD students, postdoc, we looked just at Euclid data analysis with the Euclid likelihood group, and they have the problem that MCMC just takes 3 days. And so if they add any BSM parameters, it takes much longer. So with these kind of techniques, you get the same answer in like an hour or something. That said, I'm sure if you make the MCMC thing faster, right? If you have a differential assimilated, blah, 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 you can also get quite far. Then, okay, how many modes do you have? Blah, 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 right? So it depends really on the problem.
Yeah, so I have a couple of questions. One is basically a question that you asked about the MCMCs. I mean, you mentioned them on your talk, and then it's like, how, I mean, there's no really quantitative way. You just mentioned, like days and versus hours or things like that. Is there a quantitative study of that, or is it, some initial phase, or is it obvious that your methods are, much better than MCMCs?
No, it's not obvious at all. It's very, so the reason why I didn't have one slide with, hey, that's why it's better than that, is because it's complementary, right? So there are situations where the one is clearly better than the other. Let's say you have a likelihood function with 1 million modes or stuff like this, but you only care about one parameter, and in that one direction, it's a unimodal distribution. Then ABC or simulation-based inference would be much easier because you don't have to explore the 1 million modes. But if you're in a situation where you have a unimodal distribution, maybe the likelihood function is easy. It's 100, even 10 million dimensional. Then MCMC can be fast depending.
So it's on a case-by-case basis. The second question about your truncation method. Yeah. So the doubt that comes into my mind is that you're doing that there is some, like, what I would call cherry picking involved, right? So how can you be sure that you are not going to be seeing things in the data because you cherry pick? The question that comes to my mind is like, resonance, as you can see the pentafork if you cut the data, appropriately, or if you're doing this kind of like excluding and truncating. Yeah. So what's your strategy there?
That's a very good question. So the interesting thing is, I have one slide for this, that if you look at things from a likelihood perspective, right? If you look at things from a likelihood perspective, maybe sometimes you might just have a peak somewhere, right? But from a simulation perspective, there are different ways to get to that peak, and there are easy ways and there are bad ways. So one easy way would be, okay, your data looks like this blue line, right? And the network has just to learn, okay, that's kind of how data correlates with a parameter. Then it's very hard to miss that that's the right answer. You see, it's very easy to train a dumb network and get the right answer. If you have something where just in a tiny spot of the parameter space, you have a dump, like a resonance, right? Particle physics model, it's very easy to miss that. And you would get something that can look like less. So doing the comparison between simulation and likelihood-based inference is not even possible if you write down the likelihood function, because different data might have led to the same likelihood function.
Yeah. I have a question. So, with the variational inference, and then the inference problem has a very nice explanation tied to the likelihood, right? So the inference result, combining the explanation of the data and the prior Does your like ratio estimation have a similar explanation? My second question is, I see in your paper you have shown an information bound, which is the information between the hidden variable and the data. So can you comment on the two aspects? One is likelihood, the other one is neutral information.
About the first point, so one thing that is very interesting in some sense that if you, I go back to this slide here. I didn't mention this explicitly. Oh, where is this? Sorry for jumping around. So this very first thing, posterior density estimation, I saw it here, okay? This is just derived from it. So starting point is just KL divergence, Fourier divergence. And you just make a choice about whether you calculate the divergence from like your true posterior to the fitting one or the other way around. It's not a symmetric thing. So depending on what you start with, which ordering, you either end up with elbow maximus variation inference, or you end up with your posterior estimation. So it's kind of it has a very similar starting point. Also very similar interpretation in that sense. This posterior to Fourier ratio estimation is just so one of the nasty things with posterior density estimation is that the network has to be normalized to 1. So it has to be a proper probability distribution, which is possible. There are normalizing flows. But what one can also do is use posterior to prior ratio estimation. One can simply show that this loss function leads essentially to the same answer than this thing here, except that on top of that, you also learn the normalization correctly. The interpretation of this, yes, so if you now think about what data summaries does this learn, this year would learn a data summary that optimizes the entropy of the posterior. This year learns a data summary that optimizes the Jensen-Shen divergence between posterior and prior, so maximizes it. If you think about Gaussians, it's kind of the same. There might be cases where it's not, but that's where this comes in. I hope this also answers your second.
How about information? Talking about information bound.
I don't remember that. Actually, we should talk.
Okay, we can talk.
Yeah, okay.
We're unfortunately out of time, but let's thank Christoph again.